Everyone, this is Sohith, and today I'm going to present my research project, which is TuberDock, a web-based platform for machine learning driven QSAR modeling and PIC50 prediction for Mycobacterium tuberculosis treatment. Next slide, please. So, tuberculosis is like a preventable and commonly curable disease. However, if you look at the position of TB in 2023, it was likely regained as the leading cause of death worldwide, like almost twice the deaths caused by HIV or AIDS. And it's caused primarily by Mycobacterium tuberculosis, and it continues to be a global health issue. And according to World Health Organization, the target is to end the TB epidemic by 2030. Next slide, please. So henceforth, our research is basically to employ QSAR modeling, which is quantitative structure activity relationship modeling, to compare machine learning model algorithms to identify lead compounds targeting our specific protein, which is enoyl ACP reductase, a potential target for tuberculosis. And if you look at the existing drugs in the market, there are triazoles, triclosan, and then acetamides and thiazoles and pyrols. But however, these drugs are becoming the bacteria is becoming multi-drug resistant. So that's why we have come up with this machine learning algorithm, so that we could predict bioactivity before actually entering in the lab. Next slide. So the methodology which we employed here is we have taken the data, we have collected the inhibitors from the Campbell database. It was having around 427 bioactivity records targeting EAR, which is enoyl ACP reductase, and then we have processed the data in such a way that we removed salts and small organic compounds from the data, and then we have calculated Lipinski descriptors like molecular weight, log P, and other like standard 5 descriptors, and then whatever IC50 values we are having, inhibition, concentration, we have converted into a log scale, which is PIC50, and then we have made it in such a way that 1 to 4 is basically like less bioactivity, 5 is intermediate bioactivity, and above 5 is the active state. And then we have removed the intermediate class to avoid the bias in machine learning algorithm. And then after that, we have done some exploratory data analysis to visualize how the data is looking like based on our Lipinski descriptors. And then after that, we have calculated fingerprint descriptors, which are like 880 pedal descriptors. And then using all this data, we have built a machine learning model. Like we have compared like 40 plus machine learning models, and by splitting the data into 80% training set and 20% test set. And the evaluation metrics which we have employed is R square, RMSE, and time. And then we have visualized the performance, and we have made like a web platform where you can just give your smiles of the compound, and then it gives you the predicted IC50 value. And then to further confirm that, we have performed molecular docking, and then we have performed ADMET analysis as well. So if you look at the website workflow here, you just give the input molecule in the form of smiles, okay, and then the machine learning model will predict how it is going to give the activity value, and then you get those values, and you can take those values, either dock it, perform ADMET analysis, or get straight into the lab and start working on that. Next slide, please. Yeah, so if we look at so if you look at the Lipinski descriptors, so the first one is number of hydrogen donors. So if you look at the active and the inactive, the p-value, if you look at the p-value, it's very less, so it means that there's a different distribution, so therefore we can reject the null hypothesis. And similarly, we can see for number of hydrogen acceptors, molecular weight. Next slide, please. And then log P and PIC50 value. As I said, these 5 important Lipinski descriptors we have computed before actually considering for the machine learning workflow. Next slide, please. So as I said, we have compared over 40 plus machine learning models, and the main metrics which I have used is R square, RMSE, and time. What is R square? R square is basically the proportion of the variance of the predicted activity value that could be explained by independent variables. What are those independent variables? Those are Lipinski descriptors like molecular weight, log P. These are like all independent values. So these values, how are they interpreting the change in the variance of the bioactivity value? So if you look at the R square, usually for a model, higher R square, lower RMSE is preferred. So here if we look at all the machine learning models, we can see higher R square is an NU SVR model, which is support vector regression model, and lower RMSE is also seen in NU SVR, which is NU support vector regression model. Next slide please. And also if we look at the time taken, it has taken like less than 0.1 seconds. So the x-axis is basically in terms of seconds, so it's just like matter of seconds and you get the output. Next slide please. So and then we wanted to know based on what descriptor or what fingerprint is the model making calculation. So we plotted the permutation feature importance plot, and we saw that PubChem fingerprint 385, 712, 150, 338, 374 are the major features that are actually making the model to make the guess of the predicted bioactivity value. And if you look at the molecular, like the structure, this is what you can see, like greater than or equal to any ring size 5. Like these are the structures that are actually favorable in a compound that could actually give you the favorable bioactivity value. Next slide please. And then we wanted to see how the experimental and the predicted. If we look at the most of the values are lying along the diagonal, which means that our model is favorably, relatively very good compared to other models, which is NU SVR model. Next slide please. And then so to test this, we have performed molecular docking. So to select compounds for molecular docking, we have selected diverse compounds from our active inhibitors data set, and here you can see we have selected this red color dots are basically the diversity set, and the gray circles are the active inhibitors in our data set. And then we have used the Kenneth-Stone algorithm to predict this, to take these diverse compounds from our existing data set. Next slide please. And then we have given that to our program. It's like a website, you can just log in as well right now, tuberdock.streamlit.app, and then if you give those values, it will give you like a predicted IC50 value, which is PIC50 value, and the one with the highest is like 8.0695 for Campbell 571677. And then we wanted to perform molecular docking, and you could see on the right hand side the molecular docking has been performed successfully well, and we could see some sort of hydrogen bond interaction, and there are also some other interactions as well. Next slide please. And then we have performed ADMET analysis. As we can see that it manages according to size, solubility, flexibility. It has some issue in flexibility, but apart from that, all other ADMET parameters are satisfied in this case. Next slide please. So if we look at the overall conclusion, so basically we have developed a computation pipeline for this in-oil ACP reductase, and we have used NUSVR model, and we got a PIC50 value of 8.06, and then when we did molecular docking, we got -7.7 kilocal per mole, which is like a favorable interaction with our target protein. And this is like a promising candidate, we could say, to further tests for experimental validation for potential therapeutic development. And one of the major limitations of our study, I would say, is the quantity of data, because we had like only like 400 or 412 sort of data. But if we could have more data in the Campbell database, we could have done even more better, and we could have improved our MSC and the R square values. But since we had less data, that is one of the major cons in our study. Thank you so much.